with a delay. Yeah, so it's a pretty simple how it's organized. I will just give the introduction to the power supply sequences. What kind of sorts of the sequences exists. Then just we will go on the power on implementation, so power on reset, LDOs, SMPS. Also, it will be spoken about the startup in multi-domain circuits, especially for microcontrollers, where also digital is distributed in multi-domains. And I will just show some pitfalls examples, just for very just when someone is really starting, it's just really it will be very, very useful to know what he should consider in order to not to have these traps in the circuits. Good. So why power supply sequences can be so important and why we have to take care about this? Yes, it's the first thing can be that it's when you power up your circuitry, especially in multi-domain, right? When you have only one source of the input source of the supplies. Maybe it can be a very not so dramatic because you have only one. But if you have two, and two of them is external from the two different sources, then of course how the system is starting up, how the this voltages are starting, how they will influence your chip is starting already important. Also, it will be important when it will be the circuitry powered down, right? How you will power down correctly. And during the power up, when you do not know what kind of circuitry you have, or you have to provide how steep, how slow your voltage should be raising up. Of course, it can influence your device operation, because if one domain was up and you start was something not isolated, of course you can latch something by mistake or by just accident, right? And then this latch signal or latch information is staying up and can influence your operation already. Then if you every time when you're starting your chip up or power down your chip down, so it could happen that you violate shortly, but you violate the safe operation region for the devices, so that in some months, years, the reliability can be already the topic for the device. It's just earlier happening. If you have also multi-domain system, it can create a simply latch up. Yeah, right. Because one of the supply is not available, another is available, and it can really make such situation when a lot of current is flowing. So it's extensive. So also it can happen that you stress your ESD protection devices, and this also can influence your ESD protection circuitry itself, because it can also overstress every time during the startup, so that, or power down, so that you it will not function anymore. Or yeah, it's of course it's a very pessimistic case. I don't think that we will have it in the future, but it can cause immediate failure of the device. This is much more severe. And of course, circuitry, what kind of circuitry can be affected? Every signal processing device which has a multi-domain power supply race affected. So all power supply converters. And so in principle, it's So about just a couple of the words of the latch up, just to remember, if we are working in CMOS, inverter and CMOS technology, and nowadays it's getting much more faster. The substrate is lighter. Let's say the gain of the circuitry is very big and bigger, so we are very, very susceptible to the latch up. Of course, latch up occurs when the voltages and currents level are beyond the normal operation level, and usually we do not have this, right? But if you take just simple inverter or buffer on the which is driving the output pin, then in the CMOS technology, the NMOS and PMOS can create a silicon-controlled rectifier, right? And this is just parasitic transistors, reverse biased, and due to the dynamic disturbances, large substrate currents or in end-well currents, this results in the fast transitioning of internal nodes, of causing this CCR, structure conducting. Of course, this also can damage your system or your circuitry. Yes, it's just one of the example of latch up in input-output buffer. If we have a pin, okay, so if we have a pin, and if we just, I will just took the example of the Xilinx, and so it's a possible pitfall if it's a power supply like contains core. Right, you have a core, you have I/O driver, and you have also to the spin connecting another driver, let's say an external driver. And in case is I/O is present, but core is not yet there, Q1 does not have a state, let's say, or it can start to, it depends on the resistance of Q1, so that D1, which is ESD protection diode, can start to conduct, and of course, if it's connected to the core, it's conducting. It's fully conducting, and this is just one of the risk when, of course, you're also functioning already disturbed. And it would be okay if the core already up before I/O is there, in order to give all the states for the buffer for the driver, or the core and I/O should start together, so that this is not happening, this conduction. Another risk is, for example, if external driver is not supplied, then the internal diode of the Q3 PMOS can start also to conduct. Yeah, so this is just some examples of why startup can be very, very important, and I think we already convinced. So it's another example, just also from the Texas Instruments. So that if you're again driving two, you have two drivers on a pin. So, and the I/O supply is earlier than a core supplies, and of course, again, the same problem can happen, and you can have current is flowing from one device or from peripheral to the from the buffer. So it can be really from one device to another. Yeah, and accordingly to this source, of the literature. There are some three distinguished three starting up schemes, sequences schemes: sequential one, ratiometric, and simultaneous. So from the previous examples, we also were talking about some of them. And sequential type, as the name is telling us, it's a sequentially starting up one supply, settles its final value, and gives signal OK to another power supply. So it's really sequential one. And it can happen that one or other is starting earlier or later. Another thing, when we are talking about starting up, about the startup really, and another thing is how you should organize your power down. Of course, everything is dependent on your application, about your concept of the circuitry, about what kind of use case you could have. Of course, it can be more, much more complicated, but let's assume in this lecture that the power down sequence is the same as the power up sequence. Means that it's reversed. So if the I/O is first, then this is I/O is the last one. So ratiometric sequencing, it's when the power supply start at the same time, for example, the core or I/O, and they continue to starting up with a proportion until regulation is reached. So this proportion is starting at some point to increasing, of course. And some of the, let's say, some of the sources even telling that they can recommend even that I/O pin, when I/O pin is starting up, then core should be a little bit earlier happening than I/O. Can be also such requirement to fulfill. There are also simultaneous types of power supply sequence. It's when the core and I/O should really starting the same time. The difference between the voltage should be kept really minimum as possible, and regulation should be reached at the same time, and the smallest amount of time, let's say, there is a difference. And this technique is really useful when the circuit has some sneak passes between the supply pins. And this we will also show this before this example. When we have the circuit can be draw some significant current from another one, and because some internal states are not yet defined. So so right now we are starting with implementation, how we can make this starting up of the blocks. And one of the best helper in this can be the diodes. Of course, diodes alone cannot make the sequential start or limit the voltage difference, but they can actually help us, right? And it's a simple way how to limit let's say the voltage between the power supplies, or during the startup or during this power down. And as you see on the left side, you have a Zener diode. And during the startup, when I/O starts up, then core, so they are not connected if they are starting on together. But if at some point core voltage starts power down before, then I/O, this is going down. Let's say so that if I/O voltage starts before the core voltage, then core voltage also going together with I/O going down. So if we have I/O voltage, right, and core voltage. Then the difference will be the diode of the zener in this direction, right? So, but when a core voltage starts before I/O, then I/O starts also, right, with this exactly the same difference. And for example, here on the right side example, we have two diodes. Okay, two diodes in one direction it will be limited, and one diode in another direction. Okay, it depending if we are starting up. So if 3.3 was starting up before 2.5, then 3.3 and 2.5 volt difference will be maximum two diodes, right? Of course, when we are taking the diodes in consideration for our starting up, then we have to always to consider that the current which is flowing through the diodes is okay for them. I mean that they can survive. How many cycles? 10,000 cycles per lifetime or whatever. So of course this should be considered. So this is just some examples on not on integrated circuits, just some examples on the system level. How we can actually start 2, 3 blocks together. And again, this is one of the one example from TI. We have IC3, IC2, and IC1, right? So 5 volt is coming. 5 volt is coming. And IC3 is starting up and giving the enable for IC1. IC1 starting up, right? And when it's reached a certain amount of voltage, around 1.8 volt, it's giving the voltage here of the resistor, sensing of the resistor divider. And then this IC3 is giving enable signal to IC2. So it's actually sequential startup, right? So yeah, another one, simultaneous startup. How to make that two voltages start simultaneously. So again, we have two chips, and we have one I/O and yes, on. So once 3.3 volt is starting up, so we have here R3 and C2, which is giving for this amplifier the voltage. This voltage is going up in certain amount. So is going up, and then IC1 starting up, and this dV over dt, this amplifier repeats and gives this feedback. For this T1 is the feedback, voltage is rising, so the V out has a controllable slope as well. So the 3 volt and I/O is starting up together. It's one of the example. Another example, again, based on the previous principle. So here we have to just start 2 power I/O and core. So 3.3 volt is starting up with the special slopes. Again, we have here this 3 as C2, which is giving us a slope. Over this amplifier, we repeat this slope here. We are giving the slope for the feedback, so that the output voltage compare. Yeah, okay. This amplifier, of course, always compares two voltages as this and this, and gives us to the feedback. Another thing here, it's that we have here the input voltage, and then we take this slope on this node and the slope of the output of IC2. And again, we control the startup over the D2 of the IC2 output, which is core. So I think it's a principle, it's somehow more or less understandable how you can control simultaneous startup. A sequential one. So, okay, here it is once power supply should start and give the okay for the another one, right? It's a little bit hard to understand, but okay, see here we have an input voltage, right? So here we have LDO with a pass device. So with a pass device, then we have a LDO power down, and okay, we put this in a high ohmic. What I wanted to tell here, I just have to remember. Input. Sorry, I cannot right now to comment it. I'm really sorry. What I wanted to actually to tell you that we, with the internal circuitry of this device, we can start LDO, and then by looking for the feedback, if it started up, we enable or disable the power down or power up, we enable the driver for the pass device. So this was, I think this was the topic behind, yes. So that LDO starting up, once it started up, it gives okay, enable okay for the pass device for between this pin and this pin. Yeah, again, it's just a sequential startup scenario. So yes, and again, for the microcontrollers, in the microcontrollers we have a multiple of the power domains. We have scenarios which really can be much more complicated than what we have seen before. And in microcontroller, when you starting up, you have one input voltage, and of course can be peripheral one, which you can control outside of microcontroller, or microcontroller will control it by itself. And the usual thing in the ICs, it's a sequential power scenario. Then when the one power is one power is up, so when Vin is up, it's giving you enable for the power one. Power on reset is giving you enable for another power supply, and so on. That the power on reset of the power two gives you enable for the third one, and so on. And this, of course, makes also more complicated for the microcontroller or the circuitry, where you have a GPIO pins, when you have a GTEC pins, or you have SPI controllers, or you have a quite tough requirement to achieve a power down constant current when you are in power down. Still, it says the system can be up, but state machine is not working, or some oscillators not up. Of course, here is starting be more complicated thing. And this starts to be first of all, how to organize the power and reset circuits. If you have one input which is not more than 5 volt, and your CMOS technology in 5 volt or whatever, 3 volt, 1.2, then it's easier to make power and reset block. You can just take the resistor divider, which is of course consumes current, right? You have, if you have already present VA or VB, or VB power supply, you take a comparator in this supply, and you just measure the voltage, right? So it sounds very easy. You can create also a threshold for this just by the comparator output, changing the resistor divider value so that you organize the threshold. In principle, it can be very easy, but this will work only if VA already present. You can consume current, of course. It's a certain current. I don't know how much mega ohms you can take, so that this quiescent current is very low. It's very easy here. It's very easy, right? The thing is, starts more complicated if you start to work with a high voltage, like 10 volt, 40 volt, 100 volt, 200 volt, and then starts another power on reset circuits in a play, and I call it voltage bank-up based circuit. So we just take the two PNP transistors or whatever PNP transistors it's or and bipolar transistors available in your technology, right? You make just the current is flowing, right? And we just assume that the voltage here equals delta VBE on the resistor, right? So from voltage point of view, we give a power up, power OK, and in principle the input voltage of these two comparator and of this can be the same. It can be actually different. It can be different in a way that you create a pre-regulator from VA, and this can be working from another supply, but the same power supply sequence. Another thing for the power and reset circuits, what can be also proposed, it's a current bank-up based, let's say, right? So when you compare two currents, and this current actually you can define when you will give the power OK, right? And if you have already starting up bank-up somewhere, you can create this sense current with what kind, which you push in this circuitry, and this once this current is equal, then power OK will be triggered. This is another thing. This is not so can be not so accurate, but this also makes the job for the starting up and giving the power OK signal. Another thing, it's of course it's you rely here already on a bank-up, what kind of accuracy you have, and so it's another thing if the bank-up still is available in your circuitry. Okay, this is just a combination of the circuits, what you can do for the fast and slow propagation. If you have, for example, the sense bandgap detector or based bandgap detector, you are sensing your VA, and this is you giving your OK. Then reference from VA domain starting up. You compare over the resistor divider or directly this voltage. You give OK, and you give the power up OK. Why I'm just presenting also this circuitry is just sometimes you need to really to react on to give just also fast path. If something is happening on the VA, you have undershoot. And then, of course, this undershoot is so low that you have to trigger the reset of the system. Then, of course, you need also this power OK should be give that power is not OK. And as low is still it's can of course not notice such spikes, right? If you just put just such detector. And then you need to introduce another circuitry, which is like monitoring this VA in order to give it OK or not. It's just a possibility combining this fast and slow for the power OK signal. Possibility. Again, things are also coming when you have some power domains available. You have, of course, you will have some level shifting between the domains. Of course, it's not avoidable. Then you have to enable properly level shifters, right? And also you need to, based on the on the power OK, you have to guarantee that you will not start to trigger the level shifter when the one of the power supply is not yet ready to do this. And level shifters usually is a very critical path for the digital to give some states for the circuits, or even for the analog. It doesn't matter. It's just between the domains. It's a gluing circuitry. And here is just two examples of how you could actually to organize transferring from one domain to another domain the signal. And this, so okay, we have a sense detector, whatever we will choose, band gap, whatever, resistor divider, comparator. And so you have to just tell me that we are okay, so this the voltage are okay in VB domain, right? In VB domain. Once this is okay, then level shifter in VB domain can already propagate the input voltage or to level shift the domain. Sorry, in domain to VB. Is correct? Yeah. Yeah. So then another thing, it's just you need to use isolation level shifter for this in order just to transfer input in another domain. So you have a sense detector as this telling you, okay, my input voltage is okay. Then I can activate ISO level shifter, and just some example how it could be that if you have enable from the A domain is coming up, it's enabled, then the signal from the B domain can be already transferred. If and also this, it could be of course you should be also lucky to have such a technology when all these domains are let's say not complicate your design, but this is easy example, just easy example how you can make it. If, for example, you have here 2 volt and here you have 5 volt, and still it's okay, right? So to work it. But if this is 100 volt domain and this is 1 volt domain, or vice versa, then we have to, of course, to apply different techniques. But I think this is more or less clear. First of all, you have to make sure that all your domains are up and proper enable is coming in a proper time in order to enable further the level shifter. So, yeah, when you have LDO, you can, of course, start LDO, right? You assuming that you should generate 3 volt domain, you have your already input. And this is one interesting example when you can already use the iMooX as a pass device. When input voltage is starting up, of course, this is a lockdown. This is never starting up, right? But if it's a depletion device, this is in principle starts work. Why? Because depletion has a almost, let's say, threshold. Can be minus or 0, so it starts to provide the current, and then this voltage starts to rise. Of course, when you have LDO, when you have to create one internal supply, and you will use the band gap which is starting at the same supply, it's already a bit questionable, right? Because you are starting VDD, band gap should start, your regulation loop starts. Of course, you could have some ups and downs, and I would be a little bit skeptical. Of course, it's fine. The reference is starting up, and then your regulation is loop starting up. But the regulation starts, especially when it's depletion here, it's really rising with a reference. In principle, it's okay. But once you have something happening on this VDD 3 volt domain, whatever is happening here, because it's internal, it can happen that you have a lot of current is drawing, for example, right? And you did not design for such current. Of course, this current starts to create some dips. Then you're losing for some time reference, because reference is not stable. The reference also will depend on the input voltage. And here it starts. I would be a little bit skeptical to check, but it's just one example. How really, when you really start the LDO, thinking you can start the domain, but then you have to start also band gap. Or in principle, you can also make so you have 2 band gaps. One is in another domain. If it's starting up, then you overruling one, but then you have to guarantee that this is not influenced on each other. Or inside of the band gap, you have another structure which is maybe low current, whatever. Of course, you can. The ideas can be a lot how to really implement, but if you will really take this drawing as a native drawing and start to think how to implement a 3 volt domain, for example, here from input, I would be already starting a bit skeptical, especially if you do not have a depletion. There is no go. There is no go about here. So, of course, it's also can be this circuitry can have a life. If you have an NMOS, not a depletion one, a normal one, but you have a startup circuitry. I also have seen some examples in production like this, but I also would be skeptical. What if your startup circuitry is not starting? What if, because this is a dead end, right? So this startup circuitry that should be in, making up that this at least have a threshold voltage here, right? From the ground, actually, from the input. So yeah, I would be a little bit skeptical here also about startup, but it's possible to make, because if this is a DMOS transistor, so it means that gate source is limited. Okay, drain source can be bigger, and this is limited. Then you have to limit these voltages, input and gate, output and gate in this case. So then the startup circuitry should actually watch two signals. Yeah, it's also one of the example when I would be skeptical a bit. Better maybe to use a PMOS, maybe to use a little bit different strategies, what we will speak later. But yeah, it's just one example. Okay. So another example, when we starting up, or we have some LDO regulators, and if regulator starts from some voltage to another voltage, and if we have its regulator for the external one, for the external pin, and then this voltage is fed in back to our chip or another chip. Usually C out can be really more than nanofarad, right? It can be even microfarad range. It depends. It depends what kind of application, of course. And then the LDO is should really have a current limit in order to limit the current during the startup. And better really to limit so that you also do not overheat your pass devices, right? So with this example, I just want to show that yes, you have a C out. Here you you have inherently integrated current limitation circuitry. So that so this is okay, your reference here. Sorry, this is your reference here. This is your feedback voltage, which is connected here, right? And if your pass device, assuming this is in a diode configuration, so this is a 3-stage, one stage, another stage, and this one, it's a pass device, okay? It's a 3-stage configuration. So, and when we are in a current limit, so the current through this device is flowing, and if it's 1 to X ratio, here we have 1, and we have a bias, whatever current sense, what we have to have here, right? So actually then, just because of ratio here on the output, divided by X, divided by N, if this current is the same as a sense, then we can start to limit our gate of this NMOS, so that this pass device is really limited and gives us the current what we want. And so this is really so this is a current voltage conversion. This is a PMOS and bias, which is okay. So What I also wanted to tell here by this example, when you also implement like a current limit circuitry, it can be also look a bit differently. You also have to break the loop for the current limit to check the stability. As you see here, for example, you do not see any compensation scheme only here for 0. For example, I prefer when we have a LDO, I prefer to have such structure, such topology of LDO, so that the compensation scheme it's compensating. So let's say the bandwidth of each individual blocks are so done so that we do not interact, and we have let's say we do not need compensation for that. And for example, with this topology, you do not, you have here the only 0 compensation, okay, but here there is no cap, no compensation. Then it's just that I guarantee that the bandwidth of this OTA is high enough so that if I have an external pool organized by the C out, so that it's always below, right? So that the pool is below. So that this is just also for the when you have of course it's not always possible, but you have to, as a designer, you have to really look for the different kind of topologies, really not only staying in one topology of LDO, just really diving in, and maybe you will have 1, 2, 3, 4 topologies, and then you will choose what kind of topology is the best in terms of the accuracy, DC accuracy, in terms of the compensation. Of course, it should be stable. Then, and in terms of dynamic. Because if I will start to introduce here the Miller caps, of course, everything interacts, giving me the doublet always if it's in a bandwidth, and then always gives me impact on the transient behavior. So you as a designer should always challenge yourself how I can find topology, the right topology, so that in LDO, for example, the frequency compensation is necessary, not necessary at all. But of course, it's not always easy, but it's maybe in 60-70% of LDOs, it's possible. It's really possible. But by this example, what I wanted just to tell you is that this LDO during the startup, limits the current. Fine, very good, very nice. But if this voltage of this voltage, input voltage, and this output voltage is so high, its difference is high, and if our current limitation, whatever, in milliamps, if I will take input voltage, assuming that it's an input voltage 100 volt, and I have milliamps, I have already watts, right? I have already watts. It can be some watts of the power dissipation. Then, of course, you have to ask yourself if it's really right topology, or is it just only for the startup? Sometimes you only using the LDO only for the startup, and then the output of the LDO is taken by another converter, or just taking and really supplying the chip. Sometimes also can happen some, but then for such thing, if it's permanently always conducting, you have to always also to think about the power consumption, about power dissipation, and then to limit, of course, this voltage difference. But this is a basics of LDO then, of basics of LDO design. And then is coming such thing like regulated, unregulated supplies. So if we have input voltage, right, and we have a normal DMOS transistors, normal without depletion. So what we can do in our system, we can actually organized pre-regulated voltages. This is usually they are not so very accurate. We are not talking about percentage of the accuracy. We are talking about plus minus 5 volt, plus minus whatever. But they are very good. They are bringing up the voltage down, and then we can really make regulated supplies like Reg 1, where we can start the band gap and start really the regulated, very precise power supplies. And if we are lucky, and in our technology we have a Zener diode. Not all the technologies has a Zener diode simply, but when we are talking about the high voltages, usually we have. Then we can really just organize by the resistor and diode and Zener. We just pre-buy this gate of this, let's say, NMOS transistor, and then we have a certain range of the pre-regulated voltage. It sounds easy. Of course, this then it will be always on, right? Because it will be always conducting unless the Vin is so low, so that then this transistor does not give anything, right? What it can be that when you have an input voltages up and down, and if you have to still working in this, let's say, in this region when your input voltage is still down, but you have to guarantee that you are off everything, or still the regulated voltages are there somehow, you can also introduce a charge pump. Of course, it's not from the first startup as charge pump is working, because you need all the pre-regulated voltage to start the clock, to start the biasing circuitry. But for the power down, you can already using the charge pump. And pumping these gates so that regulated voltage are still there, in order that you have still time to of your design of your blocks, or to bring them to the power down, because you derive this pre-regulated voltage to already regulated. Still, you maybe it's already not so perfect, not plus minus 1% if you want it. Maybe it's already plus minus 5%, but still it's good enough to do the job what you want. Good. So, yeah, this is a good approach for the power, especially for power dissipation in medium voltage and high voltage designs. And another design example, what I wanted actually to show you is if you have an input voltage, really from 0, whatever, a sky, whatever, and you have to generate maybe a 5 volt out of the sky, maybe let's say 100 volt if you have here. So, and you're lucky in your technology you have a depletion device. So depletion device, assuming that this is 0, it's starting up, starts to conduct. Okay, this Zener will limit simply the voltage on this gate from this node to ground to Zener clamping voltage. Okay, but in principle, you can organize that the depletion is all depletion device even always gives you some current, or it's on the range of sub-threshold, and give you some voltage here, which is below Zener, so not to really to activate the Zener all the time. And then you have, it's a first pre-regulator voltage for this gate, and then you have a normal device, which really then creates your pre-regulated domain and can give you here really milliamps, whatever, if you have to bring up. So, and here, yeah, you can limit by the diodes, resistor, yeah, this voltage. So yes. What you can also do here is just to limit if you have another branch. If you have another branch and you need to limit this voltage and that one regulator during the startup, of course you always can add your friend's diodes to really to make that they are starting up together or simultaneous in case you need really this in chip. So this is just another example with the depletion loss. Okay, doc. So, one moment. So another one, if you have a, for example, in your chip also DC-DC converters, right? What kind of techniques you can also apply there? Here it's an example of the booster transistor, of the boost system, and especially if the boost is you just have a driver inside, whatever you supplying your generation, you supply your driver, everything is fine, good. Then in principle, V out will be always present when V in is present, right? So the because you have inductor and you have a diode, so it's V out is a V in minus one diode, right? If you do not have a specific switch that really considers that this V out is at certain voltage. But then what you have to do all the time, even if the chip is not yet supplied, if not yet starting up, so you have to guarantee that this gate is somehow kept down always with a resistor or with a specific very high low ohmic transistor, so that it's kept down. It depends, of course, on your transistors here. And this is first what you have to remember. Power down or startup case for the DC-DC converter when you still do not have internal voltages, right? So that there should be the power devices should be off or on. It depends on the power supply converter. But we have to also guarantee that it's not conducting the current, not through and so on. That, for example, inductor is charged or something. Then the next time, when it's starting up, all the regulation, all the references there, current there, you can start your external supply. Then what you can introduce, it's a current limitation circuitry again, and soft start procedure. For the converters, it's easy. It depends on what kind of regulation loop you are using. Regulation loop can be digital, it can be analog. Soft start means that the duty cycle, what you apply during it's gradually increasing to what you really need. It's really from minimum can be increased to the what is defined by input and output ratio, so by really the duty cycle. So in order to go slowly up and charging. Of course, here it can interact the current limit. Once you have a soft start and procedure, usually you should not trigger your current limit, because when the power converter is not yet up, the power consumption of the whole system should not be so high, right? It should not be in the consuming so a lot. Usually it's a 1/3 during the startup. What you have to really it's just how to calculate what kind of current you have to provide. Let's say during the startup, you have to guarantee that 1/3 of the whole amount of your maximum current is given. And of course, with this current, then you have to recalculate back what kind of soft start procedure, what kind of current limit you can apply. You can also, during the startup, make the setting that current limit is lower or higher. High maybe not makes sense, but if you also concerned about the startup time, then but you do not want to to destroy all your external circuitry. Of course, this is can be very challenging, of course. And so two techniques is a soft start procedure and current limitation. In one, it's a hiccup mode, when you can actually, you're starting up, you see you still maybe could be in a soft start, you trigger current limit, then you could disable your system in order to make it that system relaxing a bit, dissipating that power. If you have maybe some temperature sensors on it, so of course it can bring so that it's temperature is cooled down and you start again your starting procedure. And this is just about converters. Okay, another thing, it's if you have for example, output stage or bootstrap output stage, when you would like to keep this node, right gate source of this the transistor should be 0. Then also during the startup, you need to guarantee that this voltage is 0. This is no way, right? Otherwise it starts to conduct. And especially this configuration, as you see, it's a buck converter. So when we have a this is usually this in output voltage is lower than input voltage. And this is another thing that during the startup we need to keep it low. Yeah, another thing. Okay, this is just when you have a lucky and you can use a PMOS. Then you just put 2 gates to VDD and VSS respectively, and then the power supply is off. And in principle, during the startup, no problem. This is also buck converter. And another buck converter example, it's switch cap DC-DC, as you see here. So we have only a 2-phase switch cap DC-DC with a flying cap and output cap. So here it's also very easy then, as we do not deal with any inductances. Here it's very easy to off all the switches. What is could be here also introduced? Usually DC-DC converter is or switch cap DC-DC converter. Usually regulation thing can be it's a frequency, right? You can change the frequency, or or you of course change the duty cycle. To change the duty cycle is more difficult with switch cap DC-DC. Usually they stay in the same duty cycle and fixed frequency, or the same duty cycle and frequency is varying. So what you can actually then in order to start up very smoothly, what you then modulate in order to give it current, right? With the frequency, with the duty cycle, but if the duty cycle is fixed, so you can modulate then the resistance of this of these switches. So it means it's so a lot of drivers here, so whatever drivers, or you can make it the same even binary weighted, and you activate them gradually so that you charge the cap slowly. Current limitation for the switch cap DC converters I did not see up to now. I do not recall right now any work with the current limit, but yeah, modulation you can make modulation like this for the startup. Next one is a digital. So we have some. I will just give you some overview what can be in a digital, not really going some in really deeply inside. But when I was working on 4 microcontroller, of course, then we have a very mixed startup procedure. You have to starting up all your pre-regulators, all regulators, and then you have to activate a state machine and firmware, right? That is your microcontroller is working. So first of all, you have off mode when everything is off, okay, and then it can be that my microcontroller has no enable signal. And for us, enable signals, then it's our input voltage. When input voltage is rising up and a certain under minimum, we start to starting up all the pre-regulators, low power band gaps, and biasing circuitry. Maybe they are not so accurate, but they do the job in order to continue, and they keep also quite the current low. Once it's coming the command or your input voltage is rising up further, in principle you can already activate the next states. One moment. Okay. This next state. In this state, for example, you are using state machine, firmware can be started. For this, you do not need all very fancy and very accurate oscillators. You can use maybe kilohertz range oscillator, and then when your system is needed to wake up, or its input voltage is raising up further, or your watchdog of state 1 is over, you can start the state 2. And then you can activate more precise band gap, megahertz range, for example. Your state machine is can start to run. You can also already to prepare all the domains so that you are fully on once this wake up event is coming, whatever its event is coming to waking up, you are functional, fully functional. So this is just example. As I was telling before, that the startup is divided in 2 parts, yeah, and in analog and digital, and usually one microcontroller is monitoring everything, monitoring redundancies, so a lot, and they monitor the first level of our input voltage, execute firmware, and they start the state machine that can already release a reset level. And then once you're up, when you are fully up, you can, if you want, you can deactivate the power domains. But of course, the activation of the power domain should be very, very carefully here. You have to deactivate all the monitoring system. You have to deactivate all the corresponded under voltage alarms, the registers, really just that it's not causing any reset, that you're going to the reset level. And usually in a digital, it's you could have several resets. You could have, let's say, analog resets, digital resets. It's analog, I mean that when digital's not yet starting or partially working or completely off. Then I'm talking about analog resets, asynchronous resets also, and digital resets. It's when partially it's up, all the domains are up, and we are just talking about some events what can clear or to restart some procedures. So in what I was talking before, yes, we in a digital domain usually we have a standby mode, and in standby mode you have to guarantee that maybe you're in a kilohertz range of the oscillator, maybe not all power domains are up, and so what should be activation of the blocks, as I already somehow mentioned in my talk, could be activating also by monitoring of the voltages or by the watchdogs or the timing. If a timeout, then you could reactivate some states, right? So this was for the standby. For wake up mode, yeah, again, wake up mode, we are preparing for the we have to be already prepared for the functional, right? And we have to be in such state then when we already consume more current, clocks are running, they can be already trimmed. And the trimming procedure usually it should be already done. The clock is prepared. All domains also prepared. And yeah, either the time is out or the power domain is up, then we can, or interrupts are coming that we have to be wake up, then we are in a functional mode. And another thing what I also wanted to tell that during the startup, sometimes some systems are using built-in self-test. And in principle, it's very interesting that built-in self-test, they're just giving to the system that your system is still functioning, still all, for example, if we will take, for example, if you will take a switch cap DC-DC, okay? Built-in self-test, what is doing there? It's just running the procedure that all the single devices, single switches are connected to the right domain, that they have the right resistance when they are on, so that they are not, they are high ohmic. If they are high ohmic, so it means that they are partially on or partially off, and it means that our circuitry is not prepared to work further. And this information could be used in a bigger system. This information could be used really to inform the core, so that one of the part is out of the order and we cannot proceed with the startup and give reset or stay reset off. So this is one thing that we have to also to consider, that sometimes the systems should also built-in self-test should be fast and give a very reliable thing about your block. And trimming, once firmware execution is done, then trim values can be already applied. And usually when you are untrimmed, let's say, LDOs, for example, could have a higher static regulation minimum and maximum. So just the higher static regulation borders, and but lower dynamic borders. But when you are trimmed, you have a better bias, better bandgap, for example, your static regulation is reduced, and then you can allow your system, LDO, or even a converter, power supply converter, so like a switch mode power supply converter, to use some more how to say this, overshoot borders or undershoot borders. So it means that when we are starting up untrimmed, we cannot perform fully for what we are designed, because our overshoot or undershoot during the dynamics for the load or line regulation, it could be really higher than what we have here. But for untrimmed, we actually can really fully regulate. We fully regulate and be in these borders, giving borders by the system. And so, when we are untrimmed, we cannot be fully loaded, let's say, or fully powerful or functioning. So we are assuming also some 1/3 of the current. The high current should be applied or should be taken by a trimmed device. When the trimmed device, then it's a fully functional. Yes, another thing about the trimming, when you are not in a such complex system like microcontroller, when everything is even trimming, you can apply over the temperature and curves. You can make them flat really over temperature, because you have a temperature sensors and trim value for even for 3 temperature. You can make really tip top, but once you are in a very easy, very simple block, but you need, usually it's you are using eFuses or OTP or some memory, and then it's just one trim value like temperature. Like room temperature, for example, and then you just guarantee by design that over temperature the clock is working. Good. This is what can be done. Another point is that synchronization of the device can be introduced usually after the startup, because synchronization frequency should be synchronized to the internal frequency, and during the startup we do not know what kind of frequency we have, right? So that's why usually synchronization is applied after the start, when it's fully on. But when you are losing the startup of when you're losing the synchronization, then to come back to the original frequency of your device, or even when you're in startup, you have one frequency and you have to go to another frequency. You also can you can also implement something like frequency steps, just to coming to the final frequency with the steps. It also can be done. Especially when you have a more higher frequency, less than a gigahertz, or when you could allow this. Okay. Yeah, and so this we were talking once with this graph. I wanted to say is just once you are functional and something really abnormal is happening, then asynchronous reset can happen, that you should go to switch off all your domains what is not and going to the pre-start condition or whatever, or off condition. And here it can be also that you start to violate maybe some things that some domains start to be on off earlier, or here is just I just wanted to tell you that if you have also asynchronous logic running, not like in a microcontroller that all the state machines are synchronous, you can guarantee all the timing. But if you have even asynchronous logic, then asynchronous logic, and if you need also to have a state machine running, and state machine just depend on some input signals, then your logic should be done based on the self-adjusted timing principles in order to avoid some stucks in the modes or glitches in the signals. There are some right now there are some asynchronous logic tools. They are not commercial one, of course, but in principle it's possible now to make the state machine without glitches, and it's very important. Not only during the startup, only also for the functional mode. For the if it's a synchronous reset is coming, it's very important that you do not have some glitches on some signals. Yeah, and coming further to the pitfalls, we already were discussing about the example of LDO, that we should really to be sure that we do not have any recursive signals, no nested circuits, like here that bandgap depends on the VDD. You are here with the NMOS starting up, you have to somehow starting up this. It's good that when you have a depletion, it's but still reference also can depend on a VDD level. If it's varies a lot, then the whole concept could be screwed. And when I was talking about the synchronous logic design, so simple design, so I also want to tell that you should not use in your logic latches or latched signals by some states or input signal combination of so that you should really to be sure that when asynchronous reset is coming, that you should always to clean up all these states of your state machine. It's very important. How to check that you're okay, you are on the right track? Of course, the trivial cases, it's just CNC simulation. Sometimes it's not possible to CNC simulation, right? You have to apply some extraordinary maybe DC sweeps. Maybe you have to on a transient to put some parasitic just to really to increase maybe offset of the input pair. Maybe you have to just put some mismatch on the passes. I was writing proof the robustness of the circuit applies the conditions outside of the spec and check where is the border. I think you will do it when you would like to really to guarantee that you have at least some margin, or to know when is your margin. Of course, you would do it and not do it only on a nominal cases, on maybe a really combination of the models is helping you here really to really to understand where is your limit. Another thing, it's it checks startup circuit like bandgap or for multiple stable points. For example, here I just put that you can put sense voltage a little bit different and to see how the currents are distributed, and if your dimensions also are okay, so that you have only one curve during the startup, that it's only crossing once, for example, when it's crossing, and not going up and down several times, so that you could have really multiple stable points. So it means that you could find maybe on simulation it's very difficult to find, but reality always finds some not the right one case when you will be stable, let's say. Again, no nested loop topologies. It's really like a recursive thing. No nested loop topologies. Better than to have a pre-regulated course supply for backup and biasing circuits. Check also direct power injection on if you have external pins, and check if you have, for example, LDO or power on reset circuitry. And sometimes even noise level or in a specific frequency domain, bandwidth can generate some signals inside of the PORs that could generate the reset. It can happen also something like this. It's also one hint when you have a power on reset circuits. And if you have a self-contained POR, so it means that POR which depends on the power supply, what is checking, right? Then all the blanking mechanism, of course, should be carefully checked on simulations. It's just one case. This is all from my side. What I wanted just to give you overview about the startup signals, about the different systems and different considerations.